Awesome. Hi, everyone. My name is Dan, and this is my colleague, also Dan. And today we will be talking about stateful protocol hunting. So just a quick game. Mark gave a challenge to the audience about his song and his walk-on song, and I managed to solve it. I would like to offer the same challenge about our song. Happy to buy you a beverage of your choice if you can identify where the song came from. The artist is deadmau5. In any case, so we're here to talk about stateful protocol hunting, what it is, why it matters, and how to do it. Before we get into the idea of using stateful protocol analysis to do some hunting, a word on finite state machines. Essentially, we found that ICS protocols are often designed and modeled after finite state machines. And if you're a computer science person, this is something that you learned in your degree. But essentially, for those who maybe haven't been exposed before, finite state machines are everywhere in our lives, in a lot of the tools and systems that we use. A finite state machine is really a list of states, a series of transitions between those states and an initial state. So we'll be using this concept to guide our hunting efforts. As an example, a traffic light. So I understand that the traffic lights are slightly different in this country, but in North America, you would have three states: a red, a green, and a yellow, and then the transitions would be, stay red for a minute, change to green for a minute, and then yellow for 10 seconds or so, and continue to cycle. So that's essentially the basic concept of finite state machines. So what is stateful hunting? The idea is to analyze how a protocol behaves on the network. And of course, we're talking about ICS protocols, and we'll give some examples of that with diagrams and everything. But we're really looking at the behavior of the protocol. So there are other approaches where you perform statistical analysis of function codes, for example. But what we're focusing on in this effort is the behavior of the protocol and how the protocol behaves. So what we found is that the behavior of the protocol can be matched again against the specification of the protocol or an established baseline of how a specific vendor's implementation of that protocol looks like. So certainly vendors implement protocols to different levels of specification, and therefore, if you analyze vendor X's implementation of the protocol, it'll differ slightly than vendor Y's implementation of that same protocol. So we've two things to go off of, certainly the adherence of the protocol against the actual specification, as well as an established baseline of that behavior, of a specific vendor's behavior. So we have two comparison points here. So how should protocol behave on the network? Our exercise and our research has been based on the IC104 protocol. So we've spoken about this before in North America, and it wasn't nearly as interesting as a room full of people who are probably a little bit more familiar with IC104. So if you're, nerding out right now, we'd be happy to chat with you later. But essentially, this is the finite state machine for the IC104 protocol. If you count them, there are 9 states, and there are 31 transitions between these 9 states. Certainly, the initial state is up here, and then you can relatively easily, due to the low complexity of the protocol, do some of this analysis by hand if you want. But certainly, as engineers, we are a little bit lazy, so we wrote some code to be able to do this analysis for us. But relatively simple, like I said, 9 states and 31 transitions between those states for IC104 specifically. Cool. So why does stateful protocol hunting matter? About a year ago, which was, I think, my second week working at Dragos, we got together in our office in Maryland, and we were working with Schweitzer Engineering Labs in the office to execute crash override against their equipment and see how the equipment would behave. And we ran into a lot of issues with the execution because the SCL gear that we were running the malware against would just send TCP reset packets back to us, and essentially would not accept the malware and the way that the malware tried to initiate a communication with the device. So it was interesting to us, and if you think about some of the other attacks that have occurred against ICS devices and protocols, a lot of times the attacks will try to hijack the communication and then start injecting their own packets into the communications. So we working with that information, started looking into the statefulness of the protocol and how we could potentially identify a compromise of that communication utilizing the statefulness of the protocol. Cool. So why Stateful Protocol Hunting matters? The idea, generally speaking, for crash override and for others has been that the malware attempts to kill the existing communication process, and the legitimate process closely or to a level that you can model adheres to the specification of that protocol. The malware then typically would spawn a new communication process and start communicating with the device at a different level of adherence of that specification. So if you're closely monitoring the number of state violations, which Dan will talk about in depth, you can see that there's a shift in the way that the protocol behaves on the network, and we think that that can indicate a potential compromise of the environment or the communication. And so I'll hand it over to Dan to talk about why and how to do stateful hunting.
Awesome, and kind of one other motivation for this is for an attacker to pull off an attack like they did in Ukraine. If they're actually going to inject into protocols, they actually have to implement them themselves. And so what Dan was saying about there's the IEC spec of how the protocol should work, then there's how the vendor actually implements it. There's a third one when you're talking about attacks, which is how did the attacker actually implement the protocol in there, and what bugs and errors did the attacker make when they implemented the protocol. Crash override, why we're using this example is this is a really good example of an attacker that does not understand IEC 104 at all. And these next kind of 2 slides are going to show just a few, and we don't want to do a post-game day analysis for them, but we do want to show some of the really easy ways to find really sloppy malware writers that are writing IEC 104 and these other protocols that don't really understand it. And so the first one we're going to talk about, as Dan said, when we were playing with crash override and firing it against our SCL gear at our lab, we also tried it against distributed TriangleWorks DTM distributed test manager. Same thing, we fired the malware up, fired it against the real hardware, and we were just getting TCP resets back. And so we're like, okay, did we set this up wrong? Do we not know how to use this kind of malware we collected? And kind of going through the debugging and getting it to work, we were like, man, they messed up one of the major parts of this implementation, and kind of how they design it has some major flaws. And so what you're seeing on the screen is like one of the first ones. So with crash override, what happens, as Dan said, is one of the options of the malware is attacker drops it on the box. They can set the command or the process name of the legitimate running process, and the malware first will kill that legitimate communications process and stand up crash override's process. Well, with how Windows works, this is really loud, because when you're tearing down and building up a process, you're generating host logs. You're also generating network logs depending on how you're actually interacting with Windows. And so with crash override, this was one of the very quick kind of things that we saw on there was that connection would come down, and the malware didn't actually know how to handle when it wasn't at the start of that. It didn't know how to set up the connection. If you're using a tool like Snort, Snort's IAC 104 engine will also find this because they look for those stop DT and start DT, basically how IAC 104 builds the connection up. Tools like Snort would find this because it looks for those session establishments. We put this in there because it's also interesting just with how whoever wrote crash override, with whoever wrote it, they didn't really account for this. So this can really be found quickly by looking for those abrupt out-of-state connections, and I'll show kind of on a diagram what that looks like on some of our output. The second one, and this one's, when I say that they really didn't understand IAC 104, this is really the area with it because, so they fall out of, as Dan showed, there's those 9 different states it should be in and the 31 ways to move from state to state. When the malware got into a bad state, it didn't know how to recover. And so it didn't know where in that state diagram or where in that kind of behavioral model it was. And so it just kept hammering on the device. It was almost like more of a denial of service than actually trying to send a legitimate command to get a legitimate action back. So with this, and when we talk about state violations, which by the way, kind of going back to the traffic light example for what a state violation is. And so like as Dan said, if you're in North America and you see a stoplight go from red to yellow, that's a state violation because the stoplight should just go from red to green, green to yellow, yellow to red. When you see an abrupt jump like that to another state, that's essentially a state violation. And in this case, when this protocol gets into that state and the malware, which has no sense of where it actually is, gets there, it doesn't know how to recover. And we never actually saw it recover when we were running it in the lab. So moving on to what that looks like. This was the output of the tool. I'll talk a little bit about, the tool and how we developed it at the end. This is what it kind of looks like. So on your far, these two right to y'all, you have state violations, resets received, the orientation that the packet was sent, and then the type of packet and requested action. This is in a good state because you can see your right columns are both zeros. So in this case, this was just IAC 104 to legitimate devices talking as they should with very close adherence to the protocol spec because you can see there's 0 violations or 0 resets. This is actually with crash override running. And so very quickly after, when you start that IAC 104 module, you begin to quickly see that state violation counter go up quick. And we'll talk about, so in one case, we had a case where we let the TCP reset happen, and then we actually have gear also where we can say, ignore the TCP reset and just keep talking. It'll just see how far it'll go without actually enforcing how the protocol could be. When you're testing malware like this, it's important to have both. Actually, on the next slide, we'll cover kind of what both of those looks like. But this allows you to kind of see the different states regardless of what the physical systems are doing. So as I said, when we were testing, we were using, so the SEL gear on the right. If you use physical hardware, again, it's going to rely on that vendor-defined protocol timeout. So IAC 104.2, an interesting thing is crash override's really slow, the 104 module. And so some of the commands that we saw were actually outside of the timeout range even. And so attackers either didn't know timing or how we were running it, just didn't get the command back in time. And so when you're running on physical hardware and testing this, you're constrained by the fact that, hey, the timeouts are going to be there. Those protocol states are going to be there. I'm going to get TCP resets back, and those responses could vary by vendor. So some vendors might allow you to do operations that you shouldn't be able to do just because they don't want to bring the production down or they don't want to risk that. There's more of a tolerance. While other vendors might be like, no, you're not talking the right protocol or the right way, and so I'm going to cut this down. The other thing you can test with, and this was just one off the web, it's a free, you can find it on SourceForge, is just a simulated IEC 104 simulator. With a lot of these simulators that you can get online, they don't really implement the protocol properly either. As I said, whatever you tell it, it'll tell you back what it thinks it should do regardless of how it's actually operating. And so this is kind of the two ways that we test, and we bring that up because as you're looking for rogue master and slave devices, if you want to do these testing, or this type of testing, you need to test on both. So let's talk about how we get there. So as Dan said, really the hardest part of doing this type of analysis and looking at the behaviors of the protocol is figuring out how should this protocol behave. And to get to this, there's a few ways you can go. So existing work. So as Dan said, for IEC 104, this was research done in Belfast in 2014. So this research has been out there. It's been out in IEEE, the whole state diagram's in an academic white paper. This was awesome for us. If there's not academic research, it gives you the state type of deal. You can go to the specs, so the IEC specs that you can buy, the IEEE specs, DNP3's in there, a lot of the other ones. You run into with specs where vendors actually don't always give you the entire kind of structure, behavior of the protocol. One example is Yokogawa. So Yokogawa, if you look at the IEC spec, most of it refers to version 1 of the protocol. If you go in the field and you actually look at Yokogawa gear, everything's tagged with 2. And a lot of what 2's added appears to be some of the signing and other kind of authentication fields. And so spec's another one where you can get diagrams like this, but you might have to go a little further to actually figure out how the protocol works and what they might not wanted to put out there. And then the third's the manual and observation. And so this is going with kind of that machine learning approach of you going out or writing code that says, okay, I'm seeing you jump from this state to this state to this state. With this, there's also the other interesting thing of seeing like what is the most frequently traveled state. You can kind of do other statistical analysis also in this area to figure out how the protocol should be behaving or how it does in real life. The problem with this, though, is it's based off observation, and so if you don't see a transition, it doesn't mean that it's not in the spec, it just means you didn't see it while you were building out this model. So it's important with this one to realize if you go the manual route or the machine learning route, it's only going to be good as the model of what you saw on you understanding this protocol. So I say all that to say the first step is building out kind of this model of how the protocol should work. Actually implementing this in code. So most universities, their computer science departments teach this in the second year. This took about a day and a half to write. It's about 300 lines of Python code in a Jupyter notebook. But it's just taking that, state model and actually putting it in a form that the computer can run analysis on it. From that, we jumped down to Wireshark, but in this case, we used a tool, open source tool out there called PyShark. It's just a wrapper for Wireshark, but this allowed us to use Python to pull out the fields that we're interested in and go through very large PCAPs. When we teach our training, we actually still have students go through by hand to show them how much of a pain it would be to do it by hand. You can do it by hand, but it takes a while, so PyShark's an awesome way to do that. That table that I showed you earlier is then the result that comes out. So as again, so you can see the state violations quickly, the resets received. We do statistics like you would see with some of Snort's 104 to see what are the different types of IEC 104 packets that you get, what are the starts, the stops, session, breakup, and teardown. And then after that, what you have to decide is when do you care as an analyst and when do you alert? And so this is where with Snort they do, as I said, they look for those session builds and teardowns. They look for type IDs. They look for function codes. Kind of the other area that we begin to look for is, okay, was there a significant decrease in some of the type ideas? What did the conformity to the protocol spec look like? And with that, that's where we set up in our lab the legitimate running IEC 104, saw the 0 violations. The minute we fired crash override, we began to see those applications, or the protocol violations spike. You might also see protocol violations spike when you do updates. And so if a vendor pushes out an update to a communication library, they could change their underlying implementation of the protocol. And so that's why we generally will use also other factors in that detection that Joe will talk about a little later, a few talks, I think 2 or 3 talks later. But with this, you can look for, was there a change in how this protocol or the quality of this protocol on our network? And then the other interesting one is rolling IOUs. And so looking for register values, something that crash override would do is it would look for what's at value 1, what's at value 2, what's at value 3. And it would scan all of them, and then it would actually write them. And so just looking for that behavior of sequential scans and then sequential writes, that's kind of another area because you expect it to jump around. So what else are we doing with this? So, we're based out of North America, and so we're looking at DNP3. DNP3 is a pretty big protocol for us, not just because it runs our grid. Unlike things like Modbus, DNP3, so it runs at 3 layers of the OSI stack. It's a pretty big protocol, the state machines that they have in the IEEE spec, pretty well built out. And it covers things like how DNP3 does authentication, how DNP3 does a lot of critical things important to the protocol. That's kind of one of the areas that we're looking at. And I'll kick it over to Dan to cover the rest.
Yeah, so DNP3, obviously, like Dan said, is our next target. I think that we'll also be interested in doing Modbus because it is a very, very simple protocol to draw the state diagram for. Certainly, collaboration with vendors. This project initially started as a collaboration with Schweitzer Engineering, so we'd be definitely interested in doing that with other vendors as well. And other ways of practically implementing this idea and this concept. Certainly, some of this is somewhat theoretical, and so we're always looking to see how we can continue to implement that and operationalize it, if you will. So, in conclusion, we hope that we've showed you guys that stateful protocol analysis is useful for analyzing protocol behaviors and how protocols communicate, ICS protocols communicate on our networks. We hope that we've also shown you guys that this analysis technique can be used to detect rogue, slave and master ICS devices in the environment, such in the crash override example. The next thing is we have to ask the hard questions as well, and I think that Joe will cover this well in terms of looking at anomalies and baselining and looking at blips of statistical analysis. Is one thing, but we think that the approach of analyzing the behavior of the protocol and the way that it should behave versus the way that it's currently behaving and how it transitions between those two certainly provides value in detecting that. And so we'd like to give a shout out to the fine researchers at the Queen's University in Belfast for their work and having done the stateful, the finite state machine for IC104. And anything you want to add?
No, I think that hits it well.
Yeah, and thank you for attending our talk. Thank you to the CS3 organizers and support staff, and thank you.
Yeah, and we'll...
Well, thank you. Thank you.
Thank you very much.
Sorry, this is for you. That's actually a diploma, so I need to give it to the right person. Right? Maybe you can figure it out later. So there are some questions for you. Are you ready?
Sure.
Yeah, some tough questions perhaps.
Let's do it.
We'll see. So the general conclusion is that state violations are a sign of sloppy programmers, which equals to sloppy attackers.
Yeah, so, and I don't think Joe will hit on this a little later. Just with how the IC104 module was written in this case, like strings were left in, a lot of the output was left in. They missed a lot of compilation dates that were, or times and dates that were 3 hours before when it was actually pushed out. So in this case, yeah, there is a theory, right? They could pretend to be sloppy just to look sloppy, but it's hard to believe that someone would put that much effort into kind of so much of what was missed. And
Yeah, I think it was just they didn't fully understand how the protocol behaved, and certainly you can imagine that, you know, if you observe the way that a protocol communicates and you send A, it returns B, then you think that that's all that there is. Sure. But in reality, there could be a lot of other conditions and transitions between the states.
Absolutely. So. Yeah, but I think there's another side of this coin, and I'll bring up another question. You haven't seen signs of the same sloppy implementation of protocol stacks from vendors as you saw in Crash Override. I mean, it's potentially possible that the vendors are also not really.
It is possible, and you know, being in North America, and a lot of our engagements. So we do service-facing work. Most of our our company's product-facing. We're mostly North America, so we don't run into a lot of IEC 104, at least in that area.
I think it was more of a general question. If you have looked at stuff that is actually directly from the vendor, wouldn't you be able to see some of these state violations anyway?
Definitely, yeah. If you profile the number of state violations over time, for example, for a specific vendor's implementation, certainly it will be a higher number of state violations over time than someone who implements the protocol, you know. So you can create profiles, and that's why it becomes interesting from a detection perspective to use that vendor's implementation and what you have in your environment, and to baseline that, and then to go from there to say if there's a drastic change of number of state violations over time, and we were theorizing for fun that it's possible that malware authors would implement the protocol specification better than the actual vendor, and therefore you would see a better less violations over time. So definitely.
It sounds like a real life scenario actually. So I'm curious to know if your tool that you're developing now to figure out from the perfect model, if you wish, if it would be possible to use that in plugfests and stuff that vendors have to try to figure out if they are compliant to a certain standard. I mean, when the vendor writes a new protocol stack, they usually try to communicate with other vendors just to see if they can actually understand each other. And usually they're just happy if they can understand each other, but if there are underlying problems on the network, they just, okay, maybe it was something else, so we just continue to run. So they don't look at this level. Mm-hmm. So would that make sense?
Yeah, and you know, our selfishness
conformance tests?
And our selfishness being on the defense side, as Dan said, we like the vendors to have a little bit of those state violations because we can look for that sophisticated attacker that's not going to go back and find all of the vendors' bugs to re-implement. And so, because it makes it more expensive if they have to implement the vendors' problems. So actually having vendors that violate it helps us.
So you can actually profile the vendor problems, right? Oh, excellent. So will this approach help detect the attack that we saw in the last presentation?
We haven't looked at S7 or S7 Plus.
Mm-hmm.
I don't think we have enough.
In theory, just play with the idea. Could it be possible?
Yeah, it would depend on the state machines, but theoretically.
Okay. All right, fair enough. So did you monitor the current state of the client master malware on the malware side or on the network? Sorry, on the client master malware side or on the network?
I'm not sure I understand the question.
Well, I think that you already answered that. I think that you monitor the network, right?
We did both.
You weren't on the devices or host themselves.
We were on both because it was running in our lab. So because we work a lot both on the host log and on the network log. So we did see both sides as we were testing.
But were that more for the development? I mean, is it possible to do this state violation entirely from a network side? Or do you need both?
If you did the capture on there, it depends on what you're pulling through your network adapter.
Yeah.
All right, but potentially, if you would be able to capture everything that goes through your NIC, then you could.
Yeah.
All right. So, will the tool be generally available?
So this is a tricky one. We want to make it generally available. The problem is this approach is also essentially a debugger for 104 malware. And so our company, like our higher-ups, made the decision that we couldn't just because attackers could easily pull it and use it to debug their 104 malware.
Yeah. They can use it themselves. I mean, that's one of the major or common problems with creating the blueprints, right? Is you should do this way, and then the attackers will use the same blueprint to match up, right? So will this type of approach or model work for other ICS protocols, and which protocols? You mentioned the MP3.
Yeah.
Have you looked at others?
Different protocols have different levels of complexity. Certainly, like we saw with 104, 9 states, 31 transitions, it's relatively easy. We haven't done a ton of research to identify the other potential candidates. We kind of went with what was relevant to us and our interests. But certainly, we're looking to apply the strategy to more.
Yeah.
The hardest part's getting the protocol spec, especially with the proprietary ones. So, and it's for all the major companies, getting the spec is sometimes the hardest part.
Oh yeah. And you're not the first one to discover that.
Yeah.
Do you think it is efficient enough to look for bad-made malware? Sorry, I'm just messing around here. So, do you think it is efficient enough to look for bad-made malware? I think that yes.
Yeah.
Okay. I'm just stepping in here, sorry. Have you implemented stateful hunting for other ICS protocols yet? Oh, sorry, that's my bad. What about 61850? The substation.
We haven't worked on that one yet, but
it's comprehensive.
It's on the target. Yeah.
It is?
Yeah.
Cool, very cool. No more questions. And we're a little early. Means longer coffee break. Thank you very much.
Thank you.
Excellent talk, thanks.